This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right, good morning, everyone. So first, I want to announce, I'm not sure whether I told you, I will be away in the last week of semester. I need to go to Germany, and head tutor will take over lectures, tutorials in that week. Now, I would try to go through lectures as much as possible for the time that I'm still here. So what I will do, I will be using the fourth lecture time, the tutorial lecture, to cover the lecture material, and then tutor can work through, the rest of the questions, like solved examples, and also exam questions closer to the end of the subject. So we will be running 4 lectures a week this week and the following 2 weeks after the break. So that's the first thing, right? So I just feel more comfortable that I present lecture material, and then questions can be dealt with by head tutors. So that's the first thing. Second thing is, yesterday I realized after several of you came and talked to me that I confused a lot of you. So I was concentrating on an example of body diagrams when I was talking about natural frequency and resonant frequency. A resonant frequency at which resonant peak happens is in general different from natural frequency. Now in that example, they're almost the same, right? But that may have confused, and I apologize. Just to give you, I've never been so busy in my life, I think. Yesterday, I started work, I was in my office at 7 a.m., I came home at 10 p.m. So, this is my second cappuccino, right? So, when you are tired, you may sort of not do your best. So I apologize. So if you notice anything strange in this lecture, please stop me, ask a question. Maybe don't trust everything I say, right? So put it this way. All right. So Cauchy principle of argument. So look, what we are doing in today's lecture is a slight detour, which will be needed for the next lecture, when I present Nyquist criterion. So we presented frequency response, we introduced frequency response, and we also talked about body diagrams, which was just a different representation of frequency response. And we will need to use frequency response in stating a stability criterion. It's called the Nyquist criterion, stability criterion, for closed-loop system stability. So in order to state and prove and understand Nyquist criterion, we need this mathematical result called Cauchy principle of argument. So I will talk about, I dedicate the full lecture to this, because if you understand this you will understand how Nyquist criterion works. So that's why I dedicate a full lecture talking all about this mathematical tool. It's not, you know, people would say, well, this is just mathematics. Actually, to understand Nyquist, you need to understand Cauchy first. And this is why we spend one full lecture doing this. All right, so I'll motivate things a bit. I already started doing that. And then I will state this Cauchy principle of argument, and I will, in the last part of the lecture, present like a prelude to Nyquist stability criterion. So I will explain roughly how Cauchy links to Nyquist. But next lecture we will study this in more detail. Okay. So and then I will, you know, just wrap up with conclusions. So that's the plan. Motivation is, I already said, this mathematical result underlies Nyquist stability criterion. Nyquist stability criterion is really important for analysis and design in frequency domain. By the way, both Bode and Nyquist were motivated by the problems of design of feedback amplifiers. If you remember, in the beginning of the subject, I presented feedback amplifier as one of the success stories, and I had some quotes, right? If you go back and look at those quotes state that the technological development, the feedback amplifier, led to mathematics, which is Nyquist criterion, Bode diagrams, Bode criteria, for analysis and design. So people realized they needed to develop mathematics in order to design an engineering sort of piece device, right? So this is Nyquist stability criterion is a stability criterion in frequency domain, and it can be restated via Bode diagrams. We won't do that, but simple versions of Nyquist can be easily sort of figured out from Bode diagrams. We won't cover these simpler versions of Nyquist. Now, once you understand Nyquist, you know, all the notions of phase margins, gain margins, you know, all these sort of essential notions in frequency domain will become very clear, right? So that's why we spend a bit of time going through Nyquist. And all right, what's the foundation for Nyquist? It's Cauchy, right? So we will now do a bit of a detour in, you know, mathematics, detour to explain this Cauchy principle of argument. All right, so a bit of history. So that's the person behind the name, French mathematician. You know, it's actually funny how, you know, Laplace, Lagrange, these guys are mixing together, talking, having coffees. You know, it's amazing how much actually knowledge was generated at that time by people like Cauchy. I mean, he studied in best schools in France, but some contributions, if you study mathematics more in depth, you know, you may recognize some of these things. The guy contributed to partial differential equations, Cauchy-Riemann equations, Cauchy sequences, all sorts of different fundamental mathematical tools and results. So, among other things, he came up with this Cauchy principle of argument. So it's a very interesting thing. So what I'll do, I'll introduce this principle through examples. And through examples, I will explain, you know, what this principle states. I'm getting a bit warm. I'll just get this through this. So, what we are dealing with here is, imagine you have a function f of s, which you can think of as a transfer function. By the way, this particular transfer function is non-causal, but that doesn't bother us now. It's just a mathematical object. So this f of s depends on s, complex variable s. So imagine now that I basically am interested in the following question. Suppose I have a closed contour in S-plane. So this C subscript S is a so-called contour. And this closed, the contour that we are considering is closed, right? And imagine that I want to basically travel on this contour, right, in S-plane, and I'm interested to understand where points of this contour map into F of S-plane. Note, F of S, whenever S is fixed, F of S is another complex number. So this basically plane is the image of the function or mapping that goes from S to F, where F is, in this case, is defined as S plus 1. So note that in this particular case, F of S is just S plus 1. So this is like a translation of every point in S-plane into a point in F-plane. Right. So what is interesting is that, for instance, if you look at this point here, minus 0.5 point, well, where does this point map to? Well, it maps to 0.5 because the value of F is minus 0.5 plus 1 because S is equal to minus 0.5 at that point. As you travel along the contour, and we typically, this is a convention, we will just decide to travel on the contour in clockwise direction. It's a convention. We can choose to do things in the opposite direction, and then statements can be modified. But, you know, let's choose for this to travel in the clockwise direction. Then we are sort of interested to see what the contour in F-plane does. Now, what's interesting in this case, this is just an example. What's interesting is that the 0, you see, this transfer function here has 1, 0 and has no poles. Right? So 0 is where? It's at minus 1. Right? When S is equal to minus 1, F of S is 0. Right? So 0 is here, and know that 0 is not enclosed, it's not inside the contour. And just let's make an observation that this contour, so points of this contour, as we are traveling in the clockwise direction, maps into this contour in F-plane, CF contour, and we are still traveling in the clockwise direction, and know that the origin here is not encircled by the contour. Origin is outside the contour. It's just an observation for time being. All right. It may seem very strange why I'm doing this, but things will become clearer hopefully by the end of the lecture. All right. So that's just the first observation. Are there any questions? Just what I'm doing here? No? All right. Here's another one. Now I'm saying, all right, let me think about another contour. So now I made the contour's radius larger, so now the radius is 1.5, before it was 0.5. Now, when I travel in the clockwise direction in S-plane, this translates into F contour that looks like this. And guess what? Now this contour encircles the origin. And note also that this contour in S-plane encircles the 0. So when we didn't encircle the 0 in the previous example, we did not encircle the origin. Now we did encircle the 0 here, and we did encircle the origin here. The origin is this point here, right? 0, 0, right? I just want you to sort of compare these two things. Go back. So we did not encircle the 0, so the contour was smaller, and then this guy did not encircle the origin. We increase the radius of this guy to encircle the 0, so we now encircle the 0, and now we do encircle the origin in F-plane. Right. These are just observations. Let's play with more examples just to see what happens. So actually, this is this example summarized. So what Cauchy's principle in this example? What Cauchy's principle states? It says when, by the way, 0 is for the same example given here, and what is plotted here are both cases that I presented earlier in one picture. So what it says here is when I'm traveling on this contour in clockwise direction and 0 is outside the contour, then as I traverse contour in F-plane, then the contour CF does not encircle the origin. So change in phase as I'm traveling around this contour will be 0 degrees. Whereas if I encircle the 0 by this contour here, then the change of phase in red circle here as I'm traveling around the contour will change by 2 pi degrees, because as I'm going, in the clockwise direction, I will make a full circle as I'm following the point, the test point as it travels on this circle. This red arrow would make a rotation of 2 pi, right? So let me just explain this a bit differently, and I think this is if you like horse races or Formula 1, right? So imagine that circles here, right, are circles that represent different tracks. And imagine that the 0 is the location of your seat. This is where you sit. So if you basically sit outside the track, so when you're looking at horses, how they are running around, they are making the full revolution around the track, full circle, full lap. You're watching, they are going in that direction, right? So they're now coming around the corner. You're watching them this way. They came this way. They are now coming back around this corner. You're looking down, and then you are going back. So what you did, you just sort of, the phase changed this way, that way, but it canceled. You went back to the same point, but you did not have to do this, right? You didn't have to rotate to see the horses, right? So when I say that we are traveling, following this contour in clockwise direction, I mean there is a test point, that's the horses, right? And the location of 0 is your seat. And then the line that connects you, your eyes, to the horses, location of horses, will be sort of moving, and it will be making a certain phase change, right? With respect to just how we define phase. So basically, for this point, the phase is basically this angle, right, between the positive real axis and the arrow, blue arrow. So as the horses move on the track, you would be moving to see them, to watch them, right? And then the phase or your position would change. But if you are sitting outside the track, the phase would just amount to 0. Now, that's the first situation. Now, suppose that your seat is inside the track. So what you would be doing then, the horses are running one lap, so you are following them, and what you've done, as they made a full lap, you rotated by 2 pi. That's what Cauchy principle says. For this simple example, for 0, you just have to rotate by 2 pi. Yes? Well, it's this is probably a typo. Sorry, no, it's not, because we measure the positive in the opposite direction. Yeah. So no, it's not. Yeah. So all right. So is this clear to everyone? So that's what happens. Yes.
So how you go by 0 radians? If you go up to the blue circle, if you go from that 0 blue up, you still have a change in the phase.
Yes, but as you rotate one full rotation, the net change of phase is whatever positive change you had the same negative change. So you came to the same point, right? So it canceled, right? As you were moving, you were doing this. But I count that as no net change in phase as I did the full rotation. So you did change, phase is changing, but the net effect amounts to 0.
Why did you change the phase for the red one? Getting 2 pi is 0 as well.
Because if you are sitting inside the track, so your seat is here, and now you're following horses on the red track, you are basically following them, and you had to rotate the full 2 pi to watch them all the time as they were moving. That's what he says, right? All right. So, what is the setting? So now that we presented 2 examples, now I want to present a general result. So it should not come as no surprise to you what the main result here says. So, but the setting is first important. So we have a closed curve CS in the S-plane that encircles Z zeros and P poles of f of S. Assume there are no poles exactly on the contour. So we avoid. So what we are doing here is you have a transfer function that has certain poles and zeros. Right? You enter poles and zeros into complex plane. And then CS is like a net. Like you throw a net, and this is, every CS is a different net. And then you may catch some of the poles and some of the zeros inside the net. You caught some fish. And only those poles and zeros inside this, contour would be relevant to what we will state next. They would be relevant to the change of phase in the F-plane. So the setting is, well, we have CS contour, we have Z zeros and P poles of f of S are inside the contour. We are assuming no zero poles, no poles on CS. Moving along CS in a defined direction, the function f of S maps CS into another closed curve CF in F-plane. And then we analyze the change in argument of F as S travels around the whole perimeter of C of S. So that's what we are doing in the examples, but now this is a general setting, right? So I can give you arbitrary f of S, arbitrary transfer function, and I'm still interested in the same question. What is the change of phase of f of S, as S moves on C of S, right? That's the general setting. So we are, now repeating things, again, if we have 0, right, that this is exactly the same as our example, except that C is now plotted here as positive. So if 0 is inside the contour, then the F changes by minus 2 pi radians. So we already analyzed this. And what is presented here is exactly what happens, as point, S travels on the contour, right, then we can see the change of phase. And then, so this was basically me sitting inside the track, right? And then I had to really rotate one full rotation. And then if I'm outside the track, then you have this, right? So you are basically looking outside, the test point moves on the track, and then what you do, you sort of looking this way, then looking that way, and then you come back to where you were, but you did not have to rotate, right, the full rotation. So in other words, if this 0 is outside the contour, then there is no change in phase overall, over one rotation. Obviously the phase changes, but the net effect for one full rotation is 0 change. So now, if we consider 2 zeros, well, we need to remember that the phase of the product, right, is the sum of the phases. So what we can do is just add effects of each 0 separately, right? So that's basically what this says. And you can actually say the same thing for arbitrary many zeros. So if one 0 is inside the contour, another is outside, the 0 inside the contour will amount to minus 2 pi change in phase of F. But then if this 0 outside will not contribute to the phase change, right? So we have 4 different cases. So you can have either minus 4 pi change when both zeros are inside the contour, or minus 2 pi where one of the zeros is inside the contour, and 0 when both zeros are outside the contour. Yeah. So suppose now you have a different example. You have 2 identical zeros and both zeros are located at -1. So you just consider s squared. So note that if we now go in the clockwise direction in S-plane, this is exactly what the image of f of s, which is s plus 1 squared, would look like in F-plane. So this is S-plane, this is F-plane. So note that the red curve here looks strange. Looks rather strange, right? And you can't really have very strange things. We will show much more complicated contours. By the way, I'm not here telling you anything about the shape of these contours. It just has to be closed. So the track that we are considering can be anything. That's a very cool general result. So you can have a very complicated track, or it can be a circle, it can be a rectangle, it can be anything. It just needs to be closed, right? So what happens when both zeros are outside? That's the blue case. The F contour turns out to be this, and know that we do not encircle 0, right? Which would amount to no change of phase, right, in F, net change of phase. But when both zeros are inside the red contour, look what happens. We encircle the origin once, look. So if I start, let's say, from this point, right, I go around and I basically would count this as one encirclement because I already had to rotate once to follow the point on the red contour. And then from this point onwards, I keep moving and then I come back. And this is another encirclement of the origin. So we are looking at encirclements of the origin. Blue does not encircle the origin because both zeros are outside blue contour in the S-plane. Red does encircle twice the origin, which amounts to -4 pi change in the phase of F. So as S moves on the CS contour, these red contours, then F phase changes by -4 pi, which is counted as the number of encirclements of the origin in the F-plane. So because number of encirclements of the origin in the F-plane is exactly the change of phase of F of S, as S travels on the contouring S-plane here. Now, if you have a single pole, right, then we need to remember that the phase of F is really like the negative of S minus P when we thought about P as a 0. So we just need to change the sign, right? So we are just relying on this relationship. So in other words, the statement is the same as what we had in the previous case, except that the change of phase would be with the opposite sign. So rather than -2 pi, we will say there is 2 pi change. And what does that amount to? It amounts to actually that now, so look now, this transfer function has a single pole. Now we are talking about a pole, very different thing from zeros. So we do the same test. Now pole is at -1. And we again have the same contours, blue and red. But now the red contour for the F-plane, encircles the origin in this direction, which is basically saying, well, there's a change of 2 pi rather than negative 2 pi. Okay? So poles are pretty much the same as zeros, just with a negative sign, like with negative of the zeros, right? So poles contribute positive encirclements, like clockwise. Note, we would count counterclockwise as positive 2 pi and clockwise as negative 2 pi. So zeros contribute to negative encirclements and poles contribute to positive encirclements. So now, what do you think would be a general result? If I have 5 zeros and 4 poles encircled by a contour, what would be the number of encirclements in the F-plane? No, I'm saying different number of poles and zeros. So let's say 4 zeros, 5 poles. positive encirclement. So what you need to do is you need to add up all these sort of contributions from each pole and each zero. Why we just add things? Because we're talking about phases. Phase of a product is the sum of phases. So that's why we just add them. And that's Cauchy's principle. Cauchy's principle says you cast the net in the S-plane, you see how many zeros and poles are inside the net, inside the contour, you count the number of poles and zeros, and that will tell you exactly the number of encirclements of this contour in F-plane, of the origin. The number of encirclements of the origin in F-plane. Either positive or negative. Right. So that's what Cauchy's principle is all about. For general transfer function, as S traverses this given contour, the total change of phase of F is basically the sum of the contributions from the zeros and poles. And we already studied what happens with zero when it's inside the contour and outside the contour. So you just apply this, general principle by adding individual contributions from each pole and each zero. Okay? So here is the general case. It says let f of s, your transfer function, be given, and let the contour in S plane be given. Closed contour, right? P is the number of poles of F within the contour. This is the number of poles we quote in our net, right? And Z is the number of zeros of F within the contour, right? So then, if we denote N as the number of encirclements of point 0, J0 by F of S, as S travels clockwise in the chosen contour CS. So what is this? This is the origin in F plane, right? This is the origin in F plane. So then Cauchy states that N is equals F minus P. So the number of encirclements, and by the way, this N can be either positive or negative, right? With a convention, right, that anti-clockwise encirclements are positive number and clockwise encirclements are negative number. So you can have N equal minus 1, which means there is one encirclement in clockwise direction. Right? You can, N can be 2, can be, so you can have, these things to be so negative, and negative means counterclockwise encirclements. So here are some more sort of fun examples taken from Ogata. What these examples show you, shape of the contour absolutely doesn't play any role in the statement of the result. So what is given here, you have a transfer function with 1 0 and 1 pole. 0 is at -1 and pole is at 1. So I chose this contour in S-plane, it's just a square, so obviously pole was caught within the contour and 0 was not caught within the contour. When you plot how this, as we are moving on this contour in clockwise direction, you see that we are moving in counterclockwise direction in F-plane. So basically each point here would map to one of the points here, right? And as we are moving around, well, this arrow would turn out to move this direction. So know that we encircled the origin in F-plane once in counterclockwise direction, meaning that the change of phase of F is 2 pi. 2 pi. Right? Because here, as I'm moving on this contour this way, well, I basically moved in the clockwise direction once. I rotated once. So note the funny shape of the contour. I don't care about the shape of the contours. The statement is still the same. It's a very powerful result, actually, when you think about it. Here's another weird contour, like, how, when you have this square encircling the zero. So it's the same transfer function. Now we do not encircle the pole, we encircle the zero. What happens now is we are moving in the opposite direction. Look at the shape of this guy. It's totally weird, right? I love these weird shapes you get. It doesn't matter what the shape is. still you encircle here the origin once in the clockwise direction, meaning minus 2 pi change in phase of f, right? So you encircle the origin once in the clockwise direction. Here's another one. Now you encircled both. You threw a net. This is a rectangle, larger net. Now both pole and 0 are inside the contour. Note what happens here. You are no longer encircling the origin. There are no encirclements of the origin, right? Which is what we stated in the general result. So what this illustrates now is a more general situation, right? That where we have both pole and 0, and we are testing different contours. We are testing the result on different examples, and every time we get the same conclusion as what Cauchy states. Here is another one. We can look at these two guys. You know, now they do not encircle neither pole nor 0, and they map into these contours here, right? And neither one of them encircles the origin, right? It's a very cool sort of result, and you know, the shapes of contours play no role right here. It can be any shape. All right. So, are there any questions regarding Cauchy?
An example of the last slide, why it is anti-clockwise?
Which one?
Yeah, this one. Why is anti-clockwise?
Why is it what?
Counterclockwise. There's a pole and 0 between the double shape.
You mean why this is moving this way?
Yes.
It's just because of the transfer functions, you know, mapping points in this sort of contour in this way, right? But what's important, don't worry about which way the arrows are pointing, up or down. What is important is that you do not encircle the origin. You do not encircle the origin. That's the important. That's what Cauchy says. He doesn't say which way arrows would go or anything. He just says you would not encircle the origin in this situation because the net effect of a pole and 0 would cancel out. One contributes 2 pi, another contributes minus 2 pi. Overall net effect is 0. And indeed, that translates into this contour here, not encircle the origin. Right? Yeah?
Is there a criteria that they should follow when selecting a contour? Or unexpected?
Very good question. When we present Nyquist criterion, we will pick a very special contour. Very, very special contour. To state a stability result, we will indeed apply Cauchy only to a very special contour. Yeah?
You know how you move the zeros to the origin? Like, you're mapping the S to, say, through, like, negative 1 to 0. If you have two zeros, say negative 1 and negative 2, where's the origin?
I don't care. I just want to see whether this contour here would encircle the origin or not. That's the only thing I care about. I'm not really, that's what I'm saying. I'm not worried about the shape of the contour and where which point maps. I don't care about that. I only care whether this contour here would encircle the origin or not. And in which way, how many times, clockwise or counterclockwise. What I'm saying is that the number of encirclements of the origin in this plane can be related to the number of poles and zeros, like the difference of poles and zeros encircled by the contour in this plane. That's all I'm saying. But where what maps, it's irrelevant. You will see that in the stability proof and result, this is irrelevant. All right? Okay. So now I want to present a prelude to the next couple of lectures. So we will have tomorrow 2 lectures where we will cover both Nyquist simple case and Nyquist more general case. So what is the prelude? Well, let me remind you that if we look at complementary sensitivity can be written in this way, where lambda 0 is the product of control transfer function and Planck transfer function. From algebra block diagram, we've seen this many times. So what is the test for stability for complementary transfer function? Well, characteristic polynomial, well, would be obviously obtained from something like this. This is not a polynomial yet because f of s is still like a transfer function, right? But I can cross multiply things to obtain characteristic polynomial. So I should say, not characteristic polynomial is, it can be obtained easily from this, this expression. So know that 1 plus lambda 0 equals 0 would give you all the poles of the complementary transfer function. So we learned via Raoult-Hurwitz criterion that the occasional poles, right, well, basically zeros of this guy will determine, stability of the complementary transfer function. So now let's just, for the sake of argument, assume that open loop transfer function, this guy lambda 0, is strictly proper. I'm just presenting a prelude to the Nyquist. So what we want to now consider, we want to consider lambda 0, which is the product of controller and plant transfer function. And I want to consider 1 plus lambda 0, which is my f of s. Right. So note that poles of lambda 0 are the same as the poles of f of s. How do I see that? Can you see that? When I simplify, so what is lambda 0? Lambda 0 is some polynomial b divided by some polynomial a. So how can I rewrite this 1 plus lambda 0? I can rewrite it as a plus b, everything divided by a. So then poles of f, which are zeros of a, of s, are the same as poles of the open loop transfer function lambda 0. Right? So that's how we can see it. But then zeros of f are the same as the poles of the complementary sensitivity. So if I look at that expression there, on top I have a plus b. Well, a plus b equals 0 are exactly the poles of the complementary system. So zeros of f are poles of the complementary system. All right. I hope that you are not getting lost here in poles and zeros. So we want to apply Cauchy principle now to this situation to analyze stability. So since open loop transfer function is assumed strictly proper, we would have as s, norm of s tends to infinity, then f of s is 1. Right. Why is this? Because lambda 0 would go to 0, and f is 1 plus lambda 0. Because you have more poles than zeros, as norm of s goes to infinity, then the denominator part dominates. So you are dividing like a constant by infinity. That's why we have just 1 left. So what we now pick, we pick a contour that encompasses right half of the S-plane. We call it the Nyquist D contour. So that's exactly going to your question, which contour do we pick? Well, this is the contour that we pick. We pick the so-called D contour. I will introduce it now. So D contour basically is in S-plane, right? And it consists of, these are the boundaries of this contour. It's the imaginary axis, right? It's the imaginary axis. And the semicircle of infinite radius. So this contour CS consists of the imaginary axis, that's this guy, and this CR, which is basically the semicircle of infinite radius. So why is right half plane so interesting? Well, if I want to basically check if the closed loop system would have any poles sitting in the right half plane. So that's basically why I'm interested in using this contour, right? Because I don't want any poles of the closed loop system to end up here. And I will show you, I will be able to check that. So, since we have that this holds, I already explained this, the whole CR, all of the contour here in F-plane collapses to the point 1, J0. Right? Because on infinite radius, norm of S is infinity, and we said whenever norm of S is infinity, then f of S maps to 1. Right? And then only mapping on CI needs to be computed. So what we need to look at, how f of j omega changes when omega goes from minus infinity to plus infinity. Why this j omega? Because the contour here is basically imaginary axis, and I go from minus, because I'm following a clockwise direction, I go from omega minus infinity to omega plus infinity. So the only guy that I need to check is what this guy is doing. So, and what is this? Now I ask you, what is this? Well, f of j omega is really frequency response of f. Right? So now you can see that frequency response of f popped up naturally if we picked this contour in complex plane. So what is the idea? So by the way, I'm presenting this as a prelude because we will repeat this several times. In 2 more lectures I will be going through this again. Right? So assume that you know the number of unstable poles of lambda 0. Know that poles of lambda 0 are the same as poles of f. We already stated that. Poles of lambda 0 are the same as poles of f. Then plot the frequency response of lambda 0 j omega. So what we are plotting is a frequency response of the open loop transfer function. If I plot that, then I already plotted f of j omega, because f of j omega is 1 plus lambda. So I just shift things by 1. Real part is just shifted by 1. And imaginary part is the same. So I will plot frequency response of lambda j omega, and count the number of encirclements of the critical point minus 1j0, which you denote as n. And then from Cauchy, we have that the number of zeros minus number of poles of f is equal to n. So z is the number of zeros of f in the right half plane. P is the number of poles of f in the right half plane. And then this is the number of encirclements. So note now what we are doing. I'm assuming that I know the number of poles. So number of poles of lambda 0 is the same of number of poles of f that are in the right half plane, that are encircled by the contour in S plane. I can plot the frequency response of lambda 0 and determine m. Actually, what I'm doing now, I'm figuring out how many times would the frequency response of lambda 0 would encircle the critical point minus 1j0 as omega goes from minus infinity to infinity. From these 2 points, I can determine z. But what is z? It's the number of zeros of f, but they are exactly the poles of the closed loop complementary transfer function. So basically, z is the number of unstable poles of the closed loop. So if I know the number of poles, unstable poles of lambda 0, and I know the number of encirclements of critical point minus 1j0 by this guy, which I can plot frequency response easily, right? Then I can determine the number of unstable poles of the closed loop transfer function. So I know this is a lot to digest in the first sort of encounter, but this is why I talk about this over several lectures. So I encourage you to, go and read on your own, so that next time I start talking about this, you are better acquainted with the concepts. Usually, by the way, I see lots of sad faces. This is the concept that students struggle most. So it does pay off to spend a few hours looking over this, reading a data book. So I definitely encourage you to do that. So by the way, so what we did today, we first said, okay, Cauchy principle underlies Nyquist, and I tried to introduce it to this, prelude, and we stated, Cauchy principle for general contours. That we saw that in Nyquist criterion, we will use a very specific contour called this D contour. Right? And what it says, if I know number of unstable open loop poles, Open loop poles are the poles of the lambda zero open loop transfer function. If I know the number of unstable poles of the open loop transfer function, and I know the number of encirclements of the critical point by lambda of j omega, as omega goes to from minus infinity to plus infinity, then I can determine the number of unstable poles of the closed loop transfer function. And I do that via Nyquist, right? Okay, so are there any questions? Yep.
What's the advantage of this stability criteria over the other ones, like
Good question. You will see later on that all the loop shaping, which is basically modifying body plot of a open transfer function to design controller, is based underlined by all of this. So we will introduce, using Nyquist plot, we will introduce the concept of gain margin, of phase margin, of peak of the sensitivity. All of these concepts will come from Nyquist criteria. Another advantage is you can experimentally determine the frequency response of your open loop. You can experimentally determine it. So if you know whether your open loop transfer function is stable, right? You determine the frequency response of the open loop transfer function, and you can check the stability of the closed loop from these two things. So from experiments, you check stability. Right? It's a very, as you go through more and more applications of this result, it will become clearer and clearer why it's important. All right, well, thank you very much for your attention, and thanks for asking questions. You have to keep me, awake.
And this one is the second order. Confused with this one.
This is what I was saying. They can be very close. Logarithmic scale, it's pretty much sort of the same in some conditions, but it does depend on So, look, I'm tired and I didn't respond to your question properly.
That's okay.
Yep.
That's a quick one. If just like this one, right? If a zero is in circle, and this one will be clockwise, right? The fs will be clockwise. What if their two are not in circle or they are both?
Sorry,
It's okay. It's okay. Just get my still have some time.
The equal numbers are in circle. What will be the fs? Do we have any convention or both is